that collisions have some interesting properties that allow us to kind of predict what's going to happen whenever we send them down. The first interesting one is that momentum is always conserved, and this is true for basically all the collisions that we're interested in. We're going to look at collisions where basically the two things are interacting with each other and with nothing else. It turns out in that case momentum is always conserved, and so that if you add up all the momentum you have at the beginning of the two objects that are running into each other, you have the same amount at the end. If you add up all the momentum of everything at the end, you get the same thing. We're going to be dealing just in one dimension, so we're not going to worry about x and y separately. We're generally going to deal with things that just collide in one dimension. In this case, what we can say is that if we take the mass times the velocity of the first object plus the mass and velocity of the second object before the collision, that's equal to the mass times the velocity of the first object plus the mass times the velocity of the second object after the collision. And that's how we're going to basically solve our problems. Again, this is kind of the basic idea of conservation of momentum. And in this case, the primes just represent the final state. Basically, we're getting too many subscripts, and if we just put I's for all initials and F for all the finals, we would just have way too many subscripts in there, and so we tend to use primes instead. You can use subscripts, initial and final, if you prefer. For right now, we're going to deal with a specific case, which is what are called elastic collisions. These are where mechanical energy is also conserved, or the kinetic energy at the beginning is equal to the kinetic energy at the end. This is true. This is generally not true of anything in reality, although it tends to be quite true if we don't lose a lot of energy to thermal energy. Good examples of this are pool balls smashing together in pool. There's some other kind of very extreme examples. Subatomic particles, when they smash together, actually collide elastically. But we're going to start with this thing. It turns out that in most cases we actually have a different example, which is inelastic collisions, which we'll be covering later. It turns out that if you take that equation up above that says that the kinetic energy at the beginning is equal to the kinetic energy at the end, it turns out that if you do some manipulation and plug that into the momentum equation, you actually get this equation, which is much easier to work with than the equation above it, which just says that v the velocity of the first in this case car minus the velocity of the second car is equal to minus the velocity of the first car minus the velocity of the second car. And in this case, we're actually doing we're making sure to include the signs of the velocities. So in other words, if the car is moving to the right, we'll make it positive. If moving to the left, it's negative. And it turns out if we use this equation down below, the last equation, in conjunction with our momentum equation, so if we use basically this guy right here and this guy right here, those two together are basically enough to solve any one-dimensional collision example that we're given. So let's go ahead and look at a couple, an example of a collision, and see if we can see how to actually make it work out. So let's look at our cars. So initially we have one car that's stationary. I'm going to call this car 2. And another car that's moving at some speed. And I've actually drawn these backwards because it turns out, I didn't tell you this ahead of time, but the first car, or the stationary car, has a mass of 83 grams. Whereas the car that was moving, there's a slide, car that was moving had a mass of 50 grams. So this guy's moving, that guy's stationary. So this is the initial picture. Then afterwards, this guy's moving at some velocity. And this guy may or may not have some velocity. If you notice, it almost had nothing. And these are the two things we're trying to find. Okay? So, let's start by looking, and the other thing that we have is that this velocity, we're just going to assume it was around 2 meters per second. So, that the initial velocity is just 2 meters per second. Okay, so how do we, so let's go ahead and do this. First, let's just look at the momentum. So, again, remember I'm a big fan of equations that we can always write down. So in this case, we can just write down P is equal to P prime, or the initial momentum is equal to the final momentum. We can also break that up into the different cars. Okay? And we can even write it as mv, so m1 v1 plus m2 v2 go to m1 v1 prime plus m2 v2 prime. The first thing you can notice is that if you remember, v2 at the beginning was equal to 0. We didn't have any velocity at the beginning, so we can already simplify our lives quite a bit. So now we have, m1 v1 is equal to m1 v1 prime plus m2 v2 prime. That's all well and good. We know the masses, we know the initial velocity. Problem is, look at our unknowns. We have two unknowns. We don't know this, and we don't know this. We don't know v1 prime or v2 prime. So that's why we now need to go to a different equation. Let's look at our energy equation. Again, energy is only conserved in what we call elastic collisions, or collisions where we haven't lost a lot of energy due to heat. That's not necessarily true in this case, but it turns out to be a pretty good assumption in this case, and we're just going to use it so we can see how we would actually go about solving this. I will say in general, with car crashes, they are not elastic. In general, car crashes are very inelastic. A lot of energy is put into bending the metal. There's lots of heat that's released. So that's not actually the case in normal car crashes. It turns out for these little matchbox cars, which don't bend a whole lot, it's roughly true. Okay, so if you remember, for the energy equations, we get something that looks like 1/2 m1 v1 squared plus 1/2 m2 v2 squared is equal to 1/2 m1 v1 prime squared plus half m2 v2 prime squared. It turns out that while this is absolutely true, this equation is a bear to work with because of all these squareds here. I'm going to go ahead and save you some work by telling you that again, this equation is equivalent to this equation, which says a v1 minus v2 is equal to minus v1 minus v2, both prime. What that actually is saying is that the relative velocity of the two switches, or the you'll kind of see how it comes out. So this helps out a lot. Again, v2 we know is 0, so that gets rid of this. This just says v1 is equal to minus v1 prime plus v2. I've just distributed that minus sign throughout. Okay, so that's about as far as we can get without doing a little bit of ugly math. I'm going to go ahead and solve for v1 in this case, so or v1 prime. We get that v1 prime is equal to v2 prime. Actually, let's solve for v2 prime. Let's do it that way. v2 prime is equal to v1 plus v1 prime. I've just moved the v1 prime over. Let's go ahead and plug that into our second equation. So let's bring this guy over. And then we get that m1 v1 is equal to m1 v1 prime plus m2. And now is where we plug in v1 plus v1 prime. Okay, I'm going to go ahead and distribute that out. Being careful to keep my primes. And I'm going to go ahead and move all my V1s to one side and keep all my V1 primes on the other side. So we end up with an M1 V1 minus M2 V1 is equal to M1 V1 plus prime plus M2 V1 prime. And then I'll go ahead and factor out a V1 on the left side and a V1 prime on the other side. So we get V1 times M1 minus M2 is equal to V1 prime times M1 plus M2. And then solving for V1 prime, which is one of the things we're interested in, we just get V1 times M1 minus M2 divided by M1 plus M2, which seems complicated, but it's all just some ugly math. But that's actually our answer. We can go ahead and plug in our numbers. So this is, and it turns out in this special case, I actually don't even need to convert my grams to kilograms because I'm dividing grams by grams. So I'll just keep it in those units. So we get, if we have 2 meters per second for the initial velocity, and then we have, which one's the heavier one? M1, or M2. So we get 50 minus 83 divided by 50 plus 83. And that's equal to V1 1 prime, and that's equal to, actually I think I'm going to need a calculator for this one, so actually go ahead and do this. We get 50 minus 83 is, that's minus 33 times 2 divided by 50 plus 83. And we get minus 0.5 meters per second for V1 prime. And then if we look at V2 prime, we can just go ahead and plug in this equation here, down here. That's just equal to V1 plus V1 prime. Basically, that's just momentum conservation. But so V2 prime is equal to 2 meters per second minus 0.5 meters per second, and we get 1.5 meters per second for V2 prime. So that's an interesting thing. What it says that basically V2, the heavier car, goes flying off at 1.5 meters per second, and V1, the initial car, the one that was moving at the beginning, bounces back slightly. That's not what we actually see in the video, but again, as I said, in our case, this wasn't actually a perfectly elastic collision. So a couple things I want to get from you. I know that people are going to be freaking out because they think, well, this looks like a crazy amount of math. It is. It's these things get to be a little ugly math-wise, but they always start from the same point, which is that we just set the momentums equal to each other. We basically make sure we're watching or careful with all of our signs. But these are the only two equations that we end up being really important after everything kind of works itself out. This kind of gives us a really good idea about how simple the physics is, but how it can actually be used to solve some really interesting results and show what the velocities are of a couple things knocking into each other. And we can do this with all kinds of different things. We can do things the same mass, different masses, all kinds of interesting things, and use to solve any kind of elastic collisions that we have.
Okay, I hope that was useful to help you solve elastic collisions. This is also a good example where looking in your book will help out. Also, there will be plenty of videos online as well. So check out anything you'd like and see if there's anything that that you find useful. And please come to class with any questions you may have.